Yes, Betelgeuse has done it again. This iconic star of the night sky has surprised astronomers, and all of us, more than once with its unpredictable behavior. Sometimes it sparks curiosity, sometimes even concern. And now, once again, we have news about it. This time, it's not something scary, but it is absolutely fascinating. It turns out, Betelgeuse is a binary star system. How did it manage to hide that secret for so long? Who's the mysterious companion? And how on earth were astronomers able to capture such a detailed, crystal-clear image of a distant stellar system? Let's dig in. Astronomers have always had a tough time understanding this star. Even something as basic as its distance from us has been a huge puzzle. The first high-precision measurements of parallax became available in the early 1990s, thanks to the launch of the Hipparcos Space Telescope. Back then, astronomers estimated Betelgeuse to be about 430 light-years away, but the margin of error was enormous. Later, more refined measurements placed it somewhere between 613 and 881 light-years from Earth. As you can see, that's still a pretty wide range. Even now, if you Google the latest estimates, you'll find that uncertainty is still very much there. So, what's the problem? Well, the thing is, Betelgeuse is a variable star. Its brightness constantly changes, which makes it extremely difficult to pin down its key properties. People have noticed this variability for thousands of years. It is, after all, one of the brightest stars in the night sky. And for centuries now, astronomers have been trying to explain what's behind its strange behavior. In recent years, the star has finally started revealing its biggest secrets. And just recently, we even got an image of at least one of the reasons behind its changing brightness. The thing is, Betelgeuse is a red supergiant. Its radius is about 700 times larger than the Sun's. If we placed it at the center of our solar system, its outer layers would probably reach all the way to Jupiter's orbit. At this late stage in its evolution, a massive star like this starts shedding huge amounts of material. In just 10,000 years, Betelgeuse can blow off around one solar mass into space. So naturally, the environment around it is wild and turbulent. Now, what looks like the surface of a red supergiant, technically the photosphere, is nothing like what we see on the Sun. Enormous convection cells lift material far above the star's surface, with different intensity in different regions. This creates a kind of asymmetry. Betelgeuse doesn't appear perfectly spherical. It looks more like a giant boiling bubble with massive surface blobs. These giant convection bubbles in its extended atmosphere can be as large as the star itself, and that's what gives Betelgeuse its odd, lumpy shape. Astronomers have been able to observe all these dynamic transformations using different telescopes at different wavelengths. And with such violent activity, it's no surprise that the star's brightness keeps changing when we view it from Earth. But here's the twist. Not all of these fluctuations are random. Astronomers notice that Betelgeuse has a few regular brightness cycles. One of them repeats roughly every 400 days. They've also spotted much longer cycles, including one that spans over 2,000 days. But until recently, no one really knew what caused those long-term changes. Then came 2019. That's when Betelgeuse did something really unexpected. It dimmed dramatically. The event made waves across the internet and was quickly dubbed the Great Dimming. Some even thought it meant the star was about to go supernova. Later, though, scientists found a more grounded explanation. Turns out, the star had ejected a huge cloud of dust that passed in front of it. That's the very same material Betelgeuse is constantly throwing off into space. As it cools down, it condenses into dust. And one such cloud likely blocked part of the star from our view. So, while the mystery of the Great Dimming was solved, it sparked a new wave of curiosity about our closest red supergiant. Many research teams went back to archival observations, trying to better understand the long-term variability, especially the strange 6-year brightness cycle that's been puzzling astronomers for years. The so-called long secondary periods, or LSPS, aren't unique to Betelgeuse. They've been observed in many other red supergiants as well, and they've been bothering astronomers since at least the 1960s. Why? Because no one could agree on what causes them. Scientists realized that multi-year cycles of brightness change were just too long to be explained by ordinary pulsations, like the simple expansion and contraction of the star's outer layers. Normally, giant stars don't take that long to pulse. So, alternative theories started to emerge. One idea was that some special mode of pulsation might exist in the outermost, loosely bound layers of the star. Another suggestion? The giant convection cells we talked about earlier. Their appearance and disappearance might take years, gradually making the star a bit brighter or dimmer over time. But the most compelling explanation, the one that kept coming back again and again, was the idea of a hidden companion in a close orbit around the star. The concept is this: a compact companion could interact with the star's extended atmosphere, compressing dust and gas into denser regions along the orbit, and those clumps could cause periodic changes in brightness when viewed from Earth. It's an elegant idea, but a tough one to prove. After all, we're talking about supergiants. Their brightness completely overwhelms any smaller companion, making them nearly impossible to see directly. Even using spectroscopy, it's hard to detect a companion. The chaotic, turbulent environment of a red supergiant creates so much noise that it masks any radial velocity signal a companion might produce. But then, in 2021, we finally got a breakthrough. A team of Polish astronomers working with the OGLE project, Optical Gravitational Lensing Experiment, combined optical and infrared observations. And what they found was stunning. They showed that many red supergiants with long-period variability also show secondary dimming events in the infrared. In other words, wherever we see these mysterious long-term brightness cycles, we also find hints of eclipses, but only in infrared. And that's extremely hard to explain, unless there's a companion involved. That discovery reignited the hunt for a companion to the legendary Betelgeuse, especially since astronomers had already suspected its existence for quite some time. In 2024, two independent teams of astrophysicists published papers that reanalyzed archival data and concluded the long secondary periods of Betelgeuse must be caused by an invisible companion. And finally, on July 21st, one of those teams, from NASA's Ames Research Center, published the first direct evidence of a second star. Yes, visual evidence. It's a stunning image. Some might say it looks almost surreal. After all, we're looking at a close binary star system located hundreds of light years away. So, how on earth did astronomers pull that off? The team, led by Steve Howell, used one of the Gemini telescopes, specifically the one on Mauna Kea in Hawaii. This is an 8-meter optical infrared observatory equipped with powerful instruments. And the key player here was a device called Allopeque, a Speckle imaging camera. So what makes Allopeque special? Its main feature is its ability to capture dual-color images with an exposure time of just 14 milliseconds. Yes, that incredibly short exposure time is the crucial part. Here's why it matters. Allopeque operates in Speckle imaging mode, which is a clever way to bypass the blurring effects of Earth's atmosphere. As you probably know, our atmosphere doesn't exactly help with astronomical observations. It causes turbulence that seriously reduces image clarity. Now, thanks to modern tech, we've developed adaptive optics, systems with flexible mirrors that adjust in real time to counteract atmospheric distortion. Thanks to that, the newest generation of ground-based telescopes may soon rival, and even surpass, space telescopes. But Speckle imaging offers another approach. Let's say a more budget-friendly one. Instead of compensating for the atmosphere in real time, you just freeze it. How? By taking ultra-short exposures, capturing the starlight in just 14 milliseconds so the atmosphere doesn't have time to smear the image. In that tiny window, the turbulence is practically motionless. It simply doesn't have time to mess with your data. Then, astronomers take hundreds or thousands of these quick snapshots and combine them using special algorithms to create one high-quality image. Of course, as you can guess, the downside is that you can't collect much light in such a short time, which means this technique doesn't work well for faint objects. But Betelgeuse? Yeah, not exactly faint. So, when you point a big telescope at a bright red supergiant, even with these short exposures, you can start to see things. Interesting things, like a companion star. The newly discovered companion of Betelgeuse is a star that's about 250 times dimmer than its massive partner. It's roughly 1.5 times more massive than the Sun, and it likely belongs to the hot, white-blue spectral class A or B. Its orbit takes it just about 4 times farther from Betelgeuse A than Earth is from the Sun. In fact, this star, let's call it Betelgeuse B, likely moves through the extended outer envelope of the red supergiant itself, literally diving into its turbulent surrounding layers. But here's where the story gets especially dramatic. The mass difference between the two stars is absolutely colossal. According to the research team, these two neighbors likely formed together around 10 million years ago. And yet, they may be at completely opposite stages of stellar evolution. Here's what that means. Betelgeuse B, the smaller star, might not have even reached the main sequence yet. In simpler terms, it might not have started hydrogen fusion in its core. Yes, after the protostar phase, a young star can stop accreting material, shed its dusty cocoon, and become visible to our telescopes. But that doesn't necessarily mean it has switched on its core fusion. Depending on its mass and metallicity, a star can stay in a sort of transitional phase, where it's still contracting and heating up, and may only be fusing deuterium, not regular hydrogen, protium. This stage is known as the pre-main sequence phase dash, a kind of stellar adolescence. And stars with about 1.5 solar masses can remain in this teenage state for tens of millions of years. Meanwhile, Betelgeuse A, the red supergiant, is thought to be 15 to 20 times more massive than the Sun. Stars that big don't waste time. They race straight to the main sequence and grow up almost instantly. But their large mass also makes them burn through their fuel much faster, meaning they speed run through all the stages of stellar evolution and reach their brilliant but short-lived endway sooner than their smaller companions. So, ironically, while Betelgeuse A is on the verge of a cataclysmic explosion, its close stellar neighbor, Betelgeuse B, might not have even fully ignited yet. But all that said, this doesn't mean Betelgeuse B is going to live a long, peaceful life. According to the researchers' models, the companion star is on a doomed trajectory. As Betelgeuse A keeps expanding, and it will, its outer envelope will continue creeping closer and closer to the smaller star. Soon, the red supergiant's gravitational pull will start exerting strong tidal forces on its companion. That will gradually alter the system's orbital dynamics, pulling Betelgeuse B into an ever lower orbit. At some point, the models predict this will happen in about 9,000 years. A phase of unstable mass transfer will begin. Material from the envelope of Betelgeuse A will start to flow onto the smaller star. But this won't be a gentle process. It will rapidly become chaotic and unstable, leading to the complete engulfment of the companion. In other words, a stellar merger. Now the good news. Researchers don't expect this to trigger a supernova or any other catastrophic explosion. Instead, they predict that a large amount of mass, equivalent to several tenths of the Sun's mass, will be ejected into space. At the same time, Betelgeuse's outer layers might start spinning faster. Still, they can't entirely rule out a more extreme outcome, one where the merger blows off the entire outer envelope of Betelgeuse, leaving behind a bare helium core orbiting with the companion star. But that's considered a less likely scenario. In any case, this act of stellar cannibalism is expected to reach its finale in about 10,000 years. And just to answer the question you're probably already thinking, no, we still don't know exactly when Betelgeuse will explode. It could be in a few tens of thousands or even hundreds of thousands of years. In cosmic terms, that's soon, but not so soon that we need to sit around waiting for it to blow any day now, as is sometimes implied. So, Betelgeuse's companion is a major discovery. And the good news is, we'll get another chance to observe it in November 2027 when it reaches maximum separation from its red supergiant host. Interestingly, the researchers believe that most red supergiants may have companions. Take Antares, for example, another nearby red supergiant. It also shows long-term brightness variations that could hint at a hidden stellar partner. In fact, it's entirely possible that many such stars not only have companions, but have already consumed them. Clearly, we need more detailed studies of systems like Betelgeuse to fully understand their complex dynamics. But one thing is certain, it's absolutely thrilling to realize that this legendary star, one of the most familiar in our night sky, has been hiding a secret this whole time. Even the stars we've studied the most can still surprise us.